Welcome protein coders, let's build some coding muscles. Today we're gonna see articulation points. But before this, I want to say please prerequisite bridges in graph topic. Okay, we have covered this previously in our playlist. Please prerequisite this. It is necessary to understand articulation points. Okay, now what are articulation points? They are the points which are on removal divides the graph into components. Let's see it with an example. We have this graph here. If I remove few points, let's say I remove this point. Okay, so this graph will be the resultant graph. If I remove this point, we have this graph. If I remove the second point, and we have this graph. You can see in the later 2 points we have 2 components, right? We got separate components, so they are articulate points. Similarly, we have one more point, this one. Okay, if we remove this, we will get 2 components. So let's see how we're gonna do it. First, if you remember in our detection of bridges, right, what we have done is we used a vector called discovery time vector. Okay, it will store the time at which, or you can say at what time the node is first discovered. Okay, and second property which we store is low. What this low vector will store is, it stores the lowest discovery time node reachable from the current node. Okay, when we found a cycle, we used to remember via this low vector. Okay, it stores the lowest discovery time node reachable from the current. So now let's perform the DFS and initialize our discovery and low vector. And when we found a cycle, at this time, what we do, we found a node which is visited, a neighboring node which is visited and which is not a parent. That means cycle detected. At this point, we are just gonna update the low of the node, right? We are remembering the discovery time of the node number 2 here. Okay, it is similar to the cases when we finding out the bridges, right? Then we update the low, and we when trace back the DFS, what we used to do, we will call DFS, and on returning while tracing back, we will update the low of node with minimum of low of node comma low of neighboring node. Okay, we are carrying on this the low of the node number 2 throughout the cycle. And if the test discovery time of node is less than equals to the low of node, then we say that we found a articulate point. If you remember in bridge detection code, this discovery time of node should be less than the low of neighbor, but here it is also equals to. You will see in a minute. So let's perform the operations, okay, and compare the discovery time and low of neighboring node. So when we reach at the node number 2, here you see the discovery time of the 2 is equals to the low of 3, but 2 is a articulate point, but it's not a part of bridge, so that's why less than equals to. Okay, then when we trace back again, the discovery time of 1 is less than the low of 2, so this will also be a articulate point. Node number 2 is also articulate point. But when you come to node number 0, it is not an articulate point, it is an edge case. Let's see it in a little bit more detail. How? So in graph number 1, if I remove the root node, I can still get a completely connected component of the graph. So this root node is not an articulate point. Similarly, in graph number 2, if I remove the root node, I can get 2 components of the graph. So it is an articulate point. So if you observe in graph number 1, the root node has only one child. Okay. And here children means the number of times you need to call the DFS to visit all the neighboring nodes of the root node. So in graph number 2, we have 2 children. Okay, 2 children, because we need to call DFS 2 times. Similarly, in graph number 3, if we call DFS, we just need to call DFS for once. So we will say it has only one child. So from here, we got a very important observation. The observation is, if the node is the parent node, I mean the root node, okay, then if it has one child, it is not an articulate point. If it has greater than one child, then it is an articulate point. So we will handle the case of parent separately in the code. Okay, so now let's see the code, how we're gonna implement this in our code. Let's initialize our timer and vector discovery time and low, and one more vector of boolean visited initialize with false. Now one more vector we will initialize with, which is boolean, to mark our articulate points. Okay, now let's start our DFS. First thing first, we'll mark visited of node equals to true and assign the discovery time and low equals to timer, and will increase the timer. Now let's traverse its adjacent nodes or neighboring nodes. If v is equals to parent, that means continue. We don't want to do anything with the parent. Or else, if the neighboring node is not parent and is visited, that means we found a cycle. Okay, this time we will not do anything, just update the low of the node. Low of u equals to minimum of low of u, comma, discovery time of v. Similar to detection of bridges. Else, what we will do is, we will just call the DFS, okay, and we will update the low of u equals to minimum of low of u, comma, low of v. Remember? And then we will check the condition for the articulation point, that if the node is not a root node and the low of v is greater than equals to discovery time of u, that means it is an articulate point. So we will mark this node in our vector true. Okay, and one more thing, we need to count the child of the parent node also, right? So we will initialize the child with 0, and whenever we are calling DFS, we will do child plus plus. We will check if parent equals to -1, that means this node is in root node, and if the count of the children of this root node is greater than 1, then we will mark this root node also as an articulate point. Okay, let's revise what we studied. Please prerequisite the bridges in graph topic. Okay, articulate points are points on which, on the removal of those points, we will get 2 or more components in a graph. Okay, then we saw a few examples of this. Then we see that we will maintain a discovery time vector and a low vector. And similarly to detection of bridges, when we check for the condition of articulation point, that discovery time of node is less than or equals to, we add a equals to here to the low of the neighboring node. Okay, then we say this point is an articulation point. Then we saw edge case for the parent nodes, right? And in that edge case, we saw that if root node has one child, then we can't say it is an articulate point. But if it has greater than one child, then we can say that it is an articulate point. Okay. In the code part also, it is very similar to the detection of bridges. We will perform our DFS, mark the node visited, assign the discovery time and low time. Then we will traverse the node, right? Traverse the neighbors. If the neighbor is parent, we will continue. If it is visited, that means we found a cycle. We will update the low of u, or else we'll increase the children count and perform DFS, update the low and check for the articulation point condition. And at the end, if the node is root and the count of children is greater than 1, then we will mark it as an articulate point. So that's it, guys. If you have any questions, please mention them into the comment box. You will find the problem and the solution link into the description box. If you don't understand, don't like, don't subscribe, but if you do, please show some support. Keep practicing, keep smiling. Thank you.